Hello everyone. In this video, I will be presenting embedding-based approaches to audio retrieval. I will first present what embedding-based audio retrieval looks like. Then I will talk about maximum inner product search, which is used to search over vectors, and vector quantization, which is used to improve the search time and efficiency of maximum inner product search. I will also present an overview of Google's now playing neural audio fingerprinter system, which is a SOTA audio retrieval system and now deployed on all Pixel phones. I will provide an overview of their model architecture, training, and search procedure. Embedding models are models which convert audio snippets, say 1 or 2 seconds of audio, to a fixed dimensional embedding, that is a d-dimensional embedding vector. The function f, which does the mapping, is implemented with neural networks. The query and database snippets are all converted to embeddings. The query metadata is then retrieved as the closest embedding in the database to query in terms of Euclidean distance. This retrieval can also be converted to finding the closest embedding in the database to query in terms of cosine similarity or dot product. This is finding the embedding in the database with which the query has the maximum inner product. We call this search maximum inner product search or MIPS. The search time complexity of MIPS is O and D, where n is the size of the database. This is because we are to calculate n dot products with n database embeddings, and all embeddings in the dot product are d-dimensional. There are two ways to make MIPS efficient. We reduce the number of items that are scored to identify the top results. This is done via partitioning the database of embeddings to k disjoint partitions, which can be done via k-means clustering and vector quantization. We can fit a k-means clustering model over the database of embeddings, and each partition is represented by a centroid. The second way is to improve the rate at which the items are scored, that is the number of search matches per second. This can be done by setting lower values of k in our k-means vector quantizer network. Now, instead of performing the search in time complexity OND, an overview of our more efficient search algorithm is as follows. We first learn a codebook of k quantizers or centroids, say via k-means clustering. And note, each codebook vector is the same dimensionality as the embeddings in the database. We assign each embedding in the database the partition to which they belong in. That is, for each embedding, we find the closest codebook vector in terms of some distance matrix, a cosine similarity or Euclidean distance. Now, given a query, we compute k dot products with the k codebook vectors instead of the n embeddings in the database in time complexity OKD. To find the dot products of the query with each of the database embeddings, we only need to find which partition each embedding falls in ON time complexity. And by embeddings, I mean the embeddings in the database. The dot product of query with each embedding is then the dot product of query with the nearest centroid to each of the embeddings. Hence, with vector quantization, the search now has a time complexity of OKD plus N, which can be made less than OND. Finding the top match now becomes finding which partition of the database our query falls into. We can consider each code word in the codebook to be a hash and codebook C to be a codebook of hashes. We can now perform locality sensitive hashing to return the partition of the database which is similar to query. So our hashing function then becomes gx equals argmax over I, the dot product of x and ci, where I varies from 1 to k. That is, the hash function returns the index of the centroid closest to x in terms of dot product. Given a query, we find which codebook member it is closest to and hence is hash. We then only return all embeddings in the database having the same hash as query, that is all embeddings near the vicinity of the closest centroid to query. Now let's see how we can run the codebook. Let E tilde n be the corresponding quantized representation of any embedding En in the database. For notational convenience, we write query embedding EQ as Q. We can construct a loss, which is an expectation over the sum of squared error between the inner product of query with each embedding in the database and the quantized representation corresponding to those embeddings. Using the properties of dot products, the term inside the summation can be rewritten as the square of the dot product of query and the vector En minus E tilde n. We can bring the expectation inside the summation and rewrite the squared dot product into its matrix form. Since En minus E tilde n, this term is independent of query, the expectation operator acts only on QQ transpose. Now, expectation of QQ transpose is an autocorrelation matrix. To simplify things, we can assume the query to be isotropic. As a result, each of the D values in the query vector, which is a vector in RD, are assumed to be sampled from independent identically distributed Gaussian distribution with zero mean and variance C. This means in the autocorrelation matrix, all the diagonal elements are the variances, which is equal to C, and all the other elements are covariances, which are equal to 0. This implies we can write the autocorrelation matrix as a constant times the identity matrix. This converts our loss to the Euclidean distance between each embedding in the database and the corresponding quantized representation. Thus, minimizing our loss is equivalent to minimizing the reconstruction errors of the database embeddings. We can call this vector En minus E tilde n as the residual error. Hence, the loss for each data point is the norm of the residual error. We observe that this loss is independent of the L2 norm of the query. Hence, we can constrain Q to have unit norm, and hence we distributed uniformly in the unit sphere in RD. We observe that our loss function is the k-means clustering objective function. We can optimize this loss and learn the codebook vectors using the EM algorithm. In step 1, the initialization step, we initialize the codebook vectors as k random data points sampled from the database. In step 2, we assign each database embedding the partition in the database corresponding to its nearest codebook vector. That is, we find which cluster each database embedding is a member of. After partition assignment of all database embeddings, in step 3, we update the codebook vectors. For each partition of the database, we find the most optimal centroid by optimizing the loss function over all data points in that partition. This has a closed form solution, which is the mean of all data points in that partition. We then keep on repeating steps 2 and 3 till we observe no more change in the codebook vectors or till some maximum iteration is reached. This algorithm is also known as the Lloyd algorithm. The sklearn library has a very optimized implementation for learning k-means clustering models. You can easily train such models over a database of vectors with just a couple of lines of code. Google Now Playing is an on-device music recognition system. This model inputs ambient audio and detects music using a music detector system. And once music is detected, it records the query and generates a single embedding for every 1 second of query. It generates embedding from the query using a neural audio fingerprinter network. These embeddings are then searched over a database of embeddings to retrieve the metadata of query. The neural audio fingerprinter network takes 1 second of audio represented as spectrogram as input. A stack of convolutional layers then encode the spectrogram to a single flattened intermediate representation, which is sent to a divide and encode module. This representation vector is divided into smaller vectors of same dimensionality. Say the representation vector is 1024 dimensional vector. It gets divided into 8 128 dimensional vectors. Each of the 8 vectors gets encoded with 2 linear layers. The 8 encoded vectors are then concatenated to form the final d-dimensional embedding. In this model, all layers except the divide and encode layers use the ALU activation and batch normalization. To perform retrieval, the full studio recordings in the database are converted to 1 second snippets with 2 consecutive snippets having a time offset of half a second. These snippets are then converted to embeddings using neural audio fingerprinter model. As we saw earlier, each second of query is encoded to a single embedding, and then we perform the search. The neural audio fingerprinter network is trained with triplets of audio snippets, where given an anchor snippet X, we have a positive snippet X plus or X positive, that is a similar snippet to anchor, and a negative snippet X negative, that is a snippet not related to anchor. Any snippet within 200 milliseconds of anchor snippet is considered as a positive. One can also generate positive snippets by applying augmentations like spec augment, like masking of spectrogram, and noise and reverberation to the anchor snippet X. Now in spec augment, given a T cross F spectrogram where T is the total number of time steps and F is the number of feature coefficients, you perform time masking where you mask spans of say 5 time steps in the spectrogram with the zero vector. That is, you take 5 consecutive feature vectors and replace those vectors with 5 f-dimensional zero vectors. And you perform feature masking where for each feature vector in the spectrogram, you replace spans of 5 feature coefficients with zero value. You can refer to the paper on spec augment for further details regarding such type of masking. You can gain further insights in mining the triplets for training our neural audio fingerprinter network from the following article. The triplets of snippets are converted to embeddings and a triplet loss with margin m and a Euclidean distance function is minimized. The search is performed in two stages. In the first stage, vector quantization is used to identify the partition of embeddings in the database close to query and return to a top k closest matches in the database. In the second stage, top 4 songs occurring in the metadata corresponding to the embeddings in the matches are identified. And then a fine-grained search is performed with all embeddings corresponding to the top 4 songs. Here, this number 4 may be any number based on your problem and based on how much time you, based on if how much you search time you want to reduce and all. What we discussed so far is useful for query by example, where the query is a noisy version of the original. Now for query by humming, the query doesn't have all the spectral information present in the original song. The query comes from a single source, that is a person humming the song, while the original may be a full-fledged multi-instrumental studio recording. To extend now playing for query by humming, all the studio recordings used to train the models are converted to pitch or note sequences using melody extraction models like Spice and Melodia, as we discussed in our node-based approaches. Now, these pitch or note sequences are then sent to tone generators to generate an audio with only melodic information coming from a single source only. The sequences may also be sent to some neural network which generates a hummed audio given a pitch or note sequence. The triplets now sampled for training the fingerprinter model are all hummed audio. The positive snippet may be generated via application of augmentations like pitch shift or tempo shift, which are normally encountered in query by humming. Given a hummed query, the search is also performed on studio recordings which are converted to hummed audios using the aforementioned techniques. Now, in the next talk, we will discuss more on how to learn better quantizers than those learned from our k-means clustering algorithm.